This is PreAP PreCalculus. This is Notes Section 1.1, Part 2. We just did a little discovery type session for the first part of the notes. The second one, let's get down to the nitty-gritty. So I've already got this written in for you. You might want to pause the video and write this stuff in as we go. But here is the rub. If you are adding a number to the outside of the function, that's a vertical translation up of that many units. If you are subtracting a number on the outside of the function, that's a vertical translation down that many units. Notice, if you had an ordered pair, the x value is not affected. This is the original x value. But the y value increases by whatever c is, or decreases by whatever c is. So in other words, if you had an ordered pair 2, 4 for the parent graph, the x value would still be 2, and the y value would be 4 plus whatever c is. If you're adding or subtracting a number inside the function, it affects it horizontally, and it goes the opposite way of what you might expect. If you're adding a number to x, we are translating it to the left that many units. If you're subtracting a number from x, you are translating it horizontally right that many units. As you would expect, this affects the x values of the parent graph, but it does not affect the y values. If you're multiplying by a negative, it's going to cause a reflection. If you multiply it on the outside, it's a vertical reflection. If you multiply it on the inside, it's a horizontal reflection. A vertical reflection affects the y value sign. It changes the sign. A horizontal reflection changes the sign of the x value. Negatives become positives, positives become negatives. We'll get to that one in a moment. Let's go down here. If you're multiplying by a number, it affects the graph with a dilation. Just 1 second, my dog's being bad. Sorry about that pause. Once again, if you're multiplying by a number, it affects by a dilation. If it's on the outside, it's a vertical dilation by a factor of whatever this number is. If it's on the inside, it's a horizontal dilation by the reciprocal of whatever that number is. So once again, things that affect the graph vertically affect y. Things that affect it horizontally affect x. One we skipped was this one here. If you have the absolute value of a function, this is a vertical reflection of any portion of the graph that's below the x-axis. So it's going to put the entire graph above the x-axis, and we'll get to see some examples of that, hopefully, and that would look like this. Let's see if we can apply what we have just learned. And I guess before we do that, let's look at some other parent graphs. This is the parent graph of a parabola, y equals x squared. Make a little table to the side just to show you where these numbers come from. Okay, x values and y values. If I put 0 in, what's 0 squared? Well, that's 0. If I put a 1 in, 1 squared is 1. If I put a 2 in, 2 squared is 4. If I put a 3 in, 3 squared is 9. That would be all the way up here someplace. I won't put that in. Now, if you put negative numbers in, if I put a negative 1 in, a negative 1 squared is still 1. If I put a negative 2 into this, a negative 2 squared is 4. Negative 3 squared is 9. There is a line of reflection, a line of symmetry for every parabola. The left and right side of that are going to be identical. I'm going to connect these. This is a parent graph of a quadratic. It is called a parabola when you graph it. Vertex is at 0, 0, the origin. We always want to keep track of that vertex because that's going to take into account all of the translating that we do. An absolute value function. Well, don't draw this first. Let me explain. What if this was just y equals x? Well, that would be a line that goes to the origin and has a slope of 1. As mentioned up here, if you have the absolute value of something, you reflect any portion of the graph that's below the x-axis. Well, this portion down here is below the x-axis. If I reflect that over the x-axis, that would look like this. So you can write this down now. This is the absolute value function. Its vertex is 0, 0. And this part on the right is the equation of y equals x with a restricted domain, that domain being 0 to infinity. And let's say that we include 0 for that. And this part over here is the line y equals negative x, and its domain goes from negative infinity to 0. So they're meeting up here at 0, 0. That's a parent graph of an absolute value function. Cubed root function. Make a little table for this. We got x, and we got the cubed root of x. I'm just going to write down perfect cubes. So 0, its cubed root is 0, vertex. 1's cubed root is 1. 8's cubed root is 2. So that would look like this. And then if we were to go a negative style, the cubed root of negative 1 is negative 1. Cubed root of negative 8 is negative 2. So this is going to look something like this. That's the parent graph of a cubed root function. A cubed function, which is this next one, we're going to take the x value and we're going to cube it. So if I put 0 in, 0 cubed is 0. If I put 1 in, 1 cubed is 1. If I put 2 in, 2 cubed is 8. If I put a negative 1 in, negative 1 cubed is negative 1. Negative 2 cubed is negative 8. So my graph's going to look like this. Now these two graphs have a special relationship, which we'll talk about later. Those are inverse functions. These are inverses of each other. We'll get into that later. A little bonus knowledge I just dropped on you. So at this point, you are to know basically 6 different parent graphs. You got cubic, cubed root, squared, absolute value, square root, and then also a linear function, which is a line. Describe how the graphs of each function will be different from the parent graphs, then graph the given function. So we are supposed to describe how they're different, and then we're supposed to graph. So we have 2 things to do. So we can list things horizontally and vertically, or we can do the really dumb teacher thing. Are there any reflections? Are we multiplying the outside by negative or multiplying the inside by negative? There are no reflections. Are there any yeah, that said that right. Are there any dilations? Are we multiplying the outside or inside by a number? The answer is no. Are there any reflections? Pardon me, are there any translations? Are we adding or subtracting numbers on the outside or inside of the function? Yes. There are 2 translations. We have a horizontal. If it's a horizontal reflection, it's typically the opposite of what you would think it is. This says +2, so we're going left 2. Vertical reflection, pardon me, a vertical translation. Sorry, I'm misspeaking a lot here. I apologize. Vertical things happen on the outside. This is a subtract 3, so we go down 3. So the parent graph for this is a parabola. Let's find the vertex first. The vertex is at -2, -3. Once you find the vertex, nothing else has changed about this. So I'm going to go from here, and I'm going to say, if I go to the right one, what's 1 squared? Well, that's 1. If I go from the vertex to the right 2, what's 2 squared? Well, that's 4. If I go to the right 3, 3 squared is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. A parabola is symmetric with respect to a vertical line that goes through the vertex. So I have a point here, and here, and here. If your graph doesn't look right and you've graphed a parabola, it isn't. You cannot fool your eyes. If the math checks out and the graph looks right, recheck your math because you likely made a mistake. Let's check out H. How does this differ from the parent graph? And the parent graph for this is an absolute value. Do we have any reflections? We sure do. We are multiplying by negative on the outside. Things that happen on the outside are vertical. So we have a reflection vertically. There's no dilations. Those are typically the hardest. We're not multiplying by number on the inside or outside. We do have some translations, though. We're going to translate horizontal left 1 and vertical up 4. On the inside affects it horizontally, on the outside affects it vertically. Things that happen horizontally are typically the opposite of what you would think they would be. Let's find the vertex. The vertex is going to be at -1, 4, which is right here. Since there's no change in dilation, that means the slopes that we're going to have for these rays are going to be the same as they normally would be. However, since there is a vertical reflection, instead of going up, we are going down. If the slope of the parent graph is 1, this one is going to be -1 over here and +1 over here. This is what the graph would look like. Just going to draw real quick what it would be if there was no reflection. It would be like this and like this. This gets reflected down and it makes those blue lines. This next one, you got to be super duper careful whenever the coefficient of x is not 1. We need it to be 1. I am not exaggerating. We need it. So this is the cubed root of -x minus 2. Then we're subtracting 3 on the outside. So what's happening? Well, this causes a horizontal reflection. We're going to translate to the right horizontally by 2. We're going to translate down 3. Try to write that as succinctly as I can. Reflect horizontal, translate right 2, down 3. Let's put the vertex on first, right 2 and down 3. That would be right here. Now the parent graph for this, normally we go right 1, up 1. Since it's a horizontal reflection, we're going to go left 1, up 1. Put a dot. In other words, the cubed root of 1 is 1. If we go to the left 8, 1, 2, 3, 4, 5, 6, 7, 8, the cubed root of 8 is 2. It's going to put a dot right here. So this is how part of it looks. And then here, if we go to the right one, the cubed root of 1 is 1. Then the cubed root of 8 is 2. That's really far to the right. We're not going to be able to fit it on there. This is the ordered pair 2, -3. If you compare this to the parent graph, hopefully you can see that the parent graph went from left to right and went up. Since this is a horizontal reflection, what was over here went over here. What was down here became over here. For the graph of a cubic function, a horizontal reflection and a vertical reflection will have the same result. P of x, once again, we really need the coefficient of x to be positive. Positive 1, as a matter of fact. So let me factor the negative out. I changed these parentheses to brackets just for visual effect. You can have those brackets as well. It's just harder for me to see when I do that. Not literally, but emotionally, it's hard for me to see. This negative is on the inside. It affects it horizontally, horizontal reflection. This subtract 4 is on the inside. That's a horizontal translation of right 4. This plus 1's on the outside. That's a translate up of 4. So we're going to have a horizontal reflection. We're going to translate right 4 up 1. Put the vertex on first. 1, 2, 3, 4. 4 right up 1. Please label that vertex. Now the parent graph for this, we go right 1 and up 1, because 1 cubed is 1. We go right 2 and up 8. 2 cubed is 8. We go left 1, down 1. The cubed root of negative 1 is negative 1. And then left 2, I said cubed root. Negative 1 cubed is negative 1. We go left 2 and down 8 because negative 2 cubed is negative 8. But since we have a horizontal reflection, where we would normally go right, we're going to go left. So instead of going to the right 1, 1 cubed is 1, we go left 1, 1 cubed is 1. Instead of going left 2 and up 8, instead of going right 2 and up 8, we go left 2 and up 8. 1, 2, 3, 4, 5, 6, 7. That puts my 8 pretty high up here. This is basically half. Then we're going to go right 1, down 1. 1 cubed is 1. Right 2, down 8. 1, 2, 3, 4, 5, 6, 7, 8. If we hadn't reflected this, it would have looked like something like this. But we did reflect it. The horizontal reflection moved this part over here and this part over here. All right, let's look at analytically how would we do such things. Table below shows ordered pairs on the graph of the function f of x that consist of line segments connecting the points in the table. Use a table to create a table of values for each function that is the transformation of the graph of f of x. So there are a bunch of segments. So there's a segment that goes from this ordered pair to this ordered pair, a segment from this ordered pair to this ordered pair, etc. So let's state, even though we don't know what the parent function for this is, we can state what we think is going on with this based upon this negative and this 2. That negative on the outside is going to cause a vertical reflection. And this 2 on the outside is going to cause a vertical translation up 2. Nothing else changes. These both are vertical things. They only affect the y value. So the original ordered pair xy becomes x isn't affected. Vertical reflection means we change the sign of y. Vertical shift up of 2 means that we're going to add 2 to the y. So once again, this is a mapping. This is the parent. This is our new graph. So without much thought, so this is f, the original function, and this is our new function g. Oftentimes in math, when we have something that's new, we call it prime. X prime and x are the same. They're not changing. So our ordered pairs are still, our x values for ordered pairs are the same as they were right here. -3, -1, 1, 3, and 5. Haven't changed. But our y primes, our new y values, are different from the originals. So it's to change the sign of y and then add 2 to it. Let's do that. Change the sign of 5 and then add 2. Change the sign of 1 and then add 2. Change the sign of -4 and add 2. Change the sign of 1 and add 2. Change the sign of 2 and then add 2. That's going to give us new y values of -3, 1, 6, 1, and 0, which means our new ordered pairs are -3, -3, -1, +1, 1, 6, 3, 1, and 5, 0. So if we were asked to graph g of x, we would put these 5 ordered pairs and draw segments between each pair of ordered pairs. Number 2. We'll write down what's happening horizontally and what's happening vertically. If you're using ordered pairs, it's better to break this stuff apart by horizontal and vertical. Horizontally, are there any reflections? No. Any dilations? Nope. Any translations? Yes. We're going to shift left 2. Vertically, there is a dilation of 3. There's no reflection, and there's a translate down 3. So dilate by a factor of 3, and then we're going to shift down 3. If we combine these two things together, the original ordered pair xy, that's going to become x minus 2, because we are shifting left 2, we're subtracting 2. And then we're going to have 3y minus 3, dilate by 3, which means times 3, and then down 3 means -3. So our new x coordinate for h is going to be the same as the original, minus 2. So if I subtract 2 from each of these, I'm going to have -3 minus 2, -1 minus 2, 1 minus 2, 3 minus 2, 5 minus 2. It's going to be -5, -3, -1, 1, and +3. For my new y value, y prime, it's going to be the original y times 3 and then subtract 3. So I'm going to have this, in each case, I'm going to have 3 times the y value minus 3. I'm just going to cheat my way through this because that's what I do. That's how I was raised, if you know what I'm saying. Gilmore. And then I'm going to put these y values in here. 5, 1, -4, 1, and 2. Let's just try to do this in our head without doing each step. 3 times 5 is 15. 15 minus 3 is 12. 3 times 1 is 3. Minus 3 is 0. 3 times -4 is -12. Minus 3 is -15. 3 times 1 is 3. Minus 3 is 0. 3 times 2 is 6. Minus 3 is 3. So my new ordered pairs are 5, 12, -3, 0, -1, -15, 1, 0, and 3, 3. Last one. we want the coefficient of x to be positive 1 every time. Let's rewrite this as q of x equals f of negative times the difference of x and 3 minus 2. Let's write down what's going to happen horizontally and vertically. Horizontal, stuff on the inside. Horizontal reflection because of this negative, and we're going to translate to the right 3. That means that we're going to take the x values that we had and change their sign, and then we're going to add 3 to it. Vertically, we're not multiplying anything on the outside, but we are subtracting 2, so we're going to shift down 2. So that means our original ordered pair xy is going to become negative x plus 3 and y minus 2. So our y prime is y minus 2. Change the sign of x and then add 3. That's going to be 3 plus 3, 1 plus 3, negative 1 plus 3, negative 3 plus 3, and negative 5 plus 3. It's going to give us 6, 4, 2, 0, and negative 2. Subtract 2 from our y values, so it's going to be 5 minus 2, 1 minus 2, negative 4 minus 2, 1 minus 2, and 2 minus 2. It's going to give us 3, negative 1, negative 6, negative 1, and 0, which gives our ordered pairs 6, 3, 4, negative 1, 2, negative 6, 0, negative 1, and negative 2, 0. We got one more page of notes. We'll round that up with the third video because it's a little different than what we just did. So this is part 2 of section 1.1, part 3 coming up.